All right, so this module is going to be on pumps and valves. We started talking a little bit about active pump and valve components in microfluidic devices in the last few slides of the previous module. So we can get into this now. With microfluidics, we need to have some type of flow control. Let's make this a little bit larger. So the things that you need to do flow control, you need to have valves and you need to have pumps. So valves prevent or block the flow of fluid from one place to another, and pumps are responsible for moving fluid from one place to another. If you have these two components, you can do some very sophisticated processing in some microfluidic devices, as we'll see. So we'll first talk about different types of valve technology and different types of pump technology. As you'll see, some of the technologies are simply miniaturizations of conventional technology. Meaning like the same types of approaches that are used in conventional devices are also used in microscale devices. Diaphragm pumps, for example, the Quake valves and pumps is a miniaturization of conventional technology. But because you're doing it in a microscale device, you're able to make many more of them and integrate many of them on a chip. I don't know what's happening here. There we go. Okay. Micropumps, same thing. There will be some types of pumps which are simply miniaturizations of conventional pumps. There are also some types of pumping mechanisms which take advantage of the microscale. So they take advantage of the high surface area to volume ratio in microfluidic devices. For example, electroosmotic flow. That is a type of pump where you just put a voltage across two ends of the channel and fluid flows through the channel. Seems like magic, but there's actually a very intuitive physical explanation for why electroosmotic flow happens. But it only happens in microscale devices because of the high surface area to volume ratio that exists in microchannels. Okay, so we're going to go through some of these valve and pump technologies. Starting with valves, there are many types of valves, and I think the first thing that's useful to do is to go over some conventional valve technologies just so we all have a starting point here. The motivation for valves, many assays require fluid handling, meaning like the transport of fluid from one chamber to another. Sometimes you want to hold fluid in a chamber, and so on. In a typical biology lab, you have a person with a pipette that's moving fluids from place to place. You have someone who's drawing your blood, drawing saliva or other bodily fluids for doing biological assays. So that type of flow control needs to be present in a microfluidic device if you want that device to be able to operate on its own. So you need these valves and pumps for controlling flow in a microfluidic device. Now, valves are classified by their ability to withstand pressure and by the response time. In other words, how quickly they can be turned on and off. The valve open, valve closed, that's the response time. And if we look at a few examples here, there's many different technologies that are used for active valves, things that can be turned on and off by some type of signal. There are the pneumatic valves that respond to gas pressure. We'll talk about those. Thermopneumatic uses some type of temperature to cause a pneumatic change. Shape memory alloys are metals that if you put a voltage on them, they change shape. Thermomechanic valves. We're not going to have time to actually talk about all of these. We're just going to focus on the ones that are more closely related to microfluidics. Electromagnetic valves, piezoelectric valves, electrostatic ones, electrochemical and chemical valves. A lot of these types of technologies have their role in microfluidic devices. We're only going to be talking about a subset of them. In terms of pressure, the ones in the orange box here are able to withstand pressures up to 100, 1,000 or even 10,000 kilopascals. These are the high pressure type things. And some other mechanisms are able to withstand lower pressures. These are the valve technologies in terms of response time. Electrostatic valves are actually the fastest. They have response times on the order of hundreds of microseconds. Piezoelectric valves a little bit slower. When you're working in the thermal domain, things tend to be a little bit slower in the milliseconds to seconds. And then slower still are things that involve chemical reactions. Electrochemical valves, which you can have electrical chemical reactions that generate bubbles, and those bubbles actually cause, as a bubble expands, it pushes fluid out of a channel. That's an example of an electrochemical pump. Those pumps are relatively slow, but they are amenable to miniaturization. So if you're designing a valve or a microfluidic chip for something, you have to consider the pressure and the response time requirements if you're going to be using valves. So here are some conventional valve technologies. It's always good to see what the rest of the engineering world uses before going into what the microfluidic world uses. So ball valves here, these are all examples of different types of valves that you can buy. Some of these are used in houses, some of them are used in plants and so on. A ball valve is relatively inexpensive type of valve that you can use, sometimes used in home piping. This has a sphere in it, and the sphere has a hole cut out in the middle here. You can see. Let's make this a little bit larger. All right, and this ball, the sphere, it rotates based on this external handle. And if it's in the off position, then this side is exposed to the fluid and it blocks the fluid flow. And if it's in this direction, it has an opening so flow can go right through. So the butterfly valve is a similar type concept. It's just you have this metal circle that's either blocking the flow or allowing the flow to pass through. This is typically used in higher pressure, larger type applications. The diaphragm valve is often used in these miniature pneumatic pressure controllers that you can get. The diaphragm valve is actually one that can be miniaturized. We'll see that the Quake valves, which are used in microfluidic devices, are this type of diaphragm valve. The diaphragm valve consists of a flexible diaphragm, which is shown in black here, and it's attached to some type of control element. That control element will push the diaphragm down. If the diaphragm is down here, obviously the flow between the left and the right portions of the channel are going to be blocked. All right, so the key part of it is a flexible diaphragm that can be controlled by some type of external means. In this case, you're using a solenoid. We'll get to that in the next slide. The needle valve is used in situations where you need very, very fine flow control. This is where you have some type of screw at the top, and that screw controls the location of this plunger here. And the plunger either allows some flow to come through or blocks it completely. If you need to proportion the amount of flow going from left to right, in other words, if you don't want on-off control, if you want to allow a portion of the flow to go through, then you use something like a needle valve. And especially in smaller devices, these types of needle valves are used. And the gate valve, this is the type of valve you might see in a large power plant where you just have a gate that's pushed down like this. All right, so these are all mechanically intuitive types of valves. Another concept with valves is something called a check valve. A check valve is something that allows flow only in a single direction. So these types of things will allow flow. So let's start with this one because this is something that all of you have in your homes. A swing type check valve is used in toilets. So if you look at the bottom of your the tank behind the toilet, you'll see that there's a swing check valve here. So this allows flow in this direction, in the upwards direction, but if you have flow in the opposite direction, that flap is going to come down on this opening and it'll basically block the flow. So this is one type of check valve or non-return valve. The diaphragm mechanism, we saw the diaphragm mechanism up here. This diaphragm mechanism could also be used in a check valve. So we have this flexible element in black here. All right, you can imagine that when the water is flowing this way, the diaphragm will open, allowing the water to pass through. And when you try to pass water in the reverse direction, the water pressure will push this diaphragm up against the flange, and this will prevent any type of water flow. Then we have like a ball check valve. A ball check valve has like a ball on a spring. Sometimes the ball is just loose on its own. And if you have flow coming in this way, the flow will push the ball away, allowing flow to pass through. And of course, if you try to pass flow in the opposite direction, it'll push the valve against the flange and prevent any flow. Okay, so these are some of the conventional valve technologies. Another important element is how do we control these valves? Okay, we need to, often in automated applications, and this goes for large-scale industrial automation. It also goes for laboratory automation. You need to have some way of turning the valves on and off through electrical signals. So that's where solenoids come in. Solenoids are electromagnets. So some of you have made electromagnets before in high school science experiments. The magnetic field, in the case of a solenoid, the magnetic field is used to push the plunger back and forth. Okay. Examples of solenoid, by the way, is your door locks in your cars. Those are often run by solenoids. It pushes the lock in one position versus the other. So this is an example of a solenoid valve. So these are the two channels. This is a 2-2 valve. Okay, a 2-2 valve has 2 ports, an inlet and an outlet, and 2 possible states. So the plunger here will either be in the push down position, and when you activate the electrical signal, it pulls the plunger up, and that allows flow. So this is an example of a normally closed valve. So when you don't apply any power to the system, there's no flow between P and A. P is the pressure port, A is the atmospheric port. I mean, the letters, the names of these don't matter very much, but you can see that the plunger's in this position, it blocks flow between P and A. So this is a 2-2 valve, normally closed. Normally open valve would be the situation where when there's no power applied, the valve is open. Now, there's also 3-2 valves. 3-2 valves is where, again, you have a solenoid, but now there's sort of 2 openings or 2 flanges. Okay, when this solenoid is in the bottom position, fluid is allowed to, or air is allowed to flow between R and A. And when the valve is activated and it moves to the up position, now you allow flow between P and A. So the 3-2 valve is used as a pneumatic. It's used as a pneumatic selector. Okay. If you have some type of pressure input at A, for example, and you want to direct that to R and direct that to P, you can do that. So solenoid valves can respond relatively quickly, greater than 10 milliseconds, less than 1 second. But electrostatic valves are obviously much faster than that. They can respond on the order of less than 1 millisecond. Solenoid valves rely on electromagnets, so they're typically high power. You have to run a lot of current through them. 0.1 amps to 10 amps is typical. They can work at relatively high pressures, like hundreds of psi. Another important parameter when we're talking about valves is what types of fluid can you run through there. Okay, a lot of valves are only designed to allow air to go through them. So they're designed for gases. Liquid pumps, you have to be a little bit more careful. And if you're working with corrosive materials like acids and things like that, then you have to be even more careful. So the material of the pump, what material is being wetted in the pump. Typically, a manufacturer will specify what materials are allowed to be wetted inside the pump. So compared to solenoid valves, piezoelectric valves are another alternative. It's the same type of idea. You still have a diaphragm or something that is pushed up against a flange to block flow. Piezoelectric devices are much faster than solenoid valves, because instead of working on the principle of electromagnets, it works on the principle of piezoelectrics. So a piezoelectric valve consists of these different parts. Let's see here, like this. It consists of a piezoelectric ceramic. So that's a material that deforms when you apply voltage across it. It also includes a voltage source, and then it includes another thin film on the other side of this. This is called a bimorph actuator. When you apply voltage to this, the piezo element will deform, but the passive element stays in the same position. So as a result, like, you know, if the piezoelectric element contracts and this thing is not, the bottom half is not affected, that's going to cause a cantilever beam made up of the two elements to basically bend up. You're creating some tension on the top half of this cantilever, and that's pulling it together, and that causes this to bend upwards when you apply the voltage. So this type of movement can be used as a way to control a valve, as you can see here on the left side. You know, if you turn on the voltage, this will open up this region, allowing fluid flow. If you apply a larger voltage, it moves up even more, allowing more fluid flow. So this is a faster alternative to solenoid valves. It's an order of magnitude less power. Actually, it says similar response time here, but some of these piezoelectric valves can actually, especially the microscale ones, they can operate much faster than the solenoid ones. So you can make that correction in your notes. It does require less power. They're smaller and lower noise, but they are a little bit more expensive than solenoids. They're actually smaller than solenoids, but because they use a piezoelectric material, that contributes to a higher cost. So the PZT materials, as we saw in the last module, PZT materials can also be used to induce vibrations. The ultrasonic actuators are also PZTs. Interesting class of materials. So at the microscale, how do we miniaturize? Well, it turns out one of the technologies, the most popular one, is the Quake valve. And the Quake valve is a miniaturization of the diaphragm valve, where a flexible diaphragm is used to block the flow between two parts of the channel. And in terms of where it falls in this map, this particular technology is a pneumatic technology. Okay. Pneumatics are being used, so this is showing a solenoid or electric plunger that's used to move the diaphragm back and forth. But in this case, a gas pressure coming from the top is used to bend the diaphragm back and forth. All right, so this is the details on how the Quake valves work. These are some of the landmark papers in the microfluidics field. Probably some of the most, you know, if you were to look at the top 10 papers or top 20 papers in the field, this paper would be one of them, and this one would probably also be in the top 20. And so in the notes I've included links in here, so you can click on them to see them. Now, these links go to the respective journals, so you will have to be on campus in order to access those links. If you're accessing from off campus, you have to turn on your VPN in order to access those articles. But if you're interested in this kind of stuff, these are very interesting papers from Stephen Quake's group, who's one of the very well-known people in the microfluidics field. He used to be at Caltech. He's now at Stanford. So he came up with a way to create valves in microfluidic chips. And the way that he did it is by using a multi-layer soft lithography. So the multi-layer soft lithography includes 2 layers of PDMS, one thin layer and then one standard thickness layer. They're bonded together. Okay, so what you end up getting is, oops. This is sort of the cross section. This is not from the paper, by the way. This is from Albert Folk's book. So the channel shown in orange is called the pneumatic control channel, and the white, the clear channels here are the actual microfluidic channels where the fluid is going through. So there's a fluid layer, and then there's a gas or pneumatic control layer. When you put pressure, okay, so there's actually 2 inlets here. You know, there'll be an inlet for all the liquids to go through the microfluidic chip. That will be connected to the bottom layer. There'll be a separate inlet here, which is connected to a gas input. The gas can either be switched from high pressure or to low pressure. When the gas is at high pressure, this thin region in the middle, I forgot to mention, this thin thing in the middle is PDMS, but it's a thin layer of PDMS. One of the big Advantages of PDMS in terms of material properties is that it is flexible. Okay, we talked about PDMS and why it's used a lot in microfluidics. One of the big things turns out to be is that its flexibility allows you to make these deformable elements, deformable valves. PDMS is an elastomer, so it's like a rubbery kind of material. So especially when you have very, very thin layers of this stuff, it deforms relatively easily. At something like 5 to 10 psi, you can cause these membranes, these little valves, to deform into the bottom. And when they do deform like this, the channel is going to be blocked, so no flow will happen through this channel. All right, so they take this concept into something that looks like this, where you have a fluid channel at the bottom, and then you have control channels at the top. Okay, these green channels are channels where the air can flow in. Okay, if the air pressure is high, in any one of these channels, then that respective channel is going to cause a deformation at the intersection, and that little membrane is going to push into the fluid channel, which is shown in gold, and that's going to block the fluid flow. Okay, so in this case, this particular fluid channel has 3 possible control elements on top of it. If any one of these guys are pressurized high, it's going to block the flow at that position. Okay, this is another diagram showing the same thing. This is an actual picture of a microfluidic device. This is the, when you look at it from the top view, because PDMS is transparent, you can see both of the layers. And so this is the control layer, and this is the fluid flow layer. Okay, so this is the multi-layer soft lithography. I'll show you a little bit about how that's made in a second. Now, why would you want to have three successive valves over a same microfluidic channel? Well, one thing you can do is peristaltic pumping. So in the last module, remember I showed you that that circular region, you can pump liquids through that circle to get the mixing to happen. Well, you need to have three valves which are being activated in succession with one another. We'll get to that when we start talking about pumps. That can allow you to to pump fluid through the channel. And in fact, this is what was shown here. This is the frequency of the actuation versus the pump rate. So valves and pumps are included in the same module here because, in this case, you can see that they go hand in hand. They're both fluid control elements. This information was from the Stanford Microfluidics Foundry, so you can see the cross-section of what these channels look like. Oops. Let's look at each one of these in turn. There's 4 types of pumps, or 4 types of PDMS Quake valves. These are the 2 most common ones, but let's look at this one first. This is called the push-down valve. This is made from 2 layers of PDMS. We've already talked about soft lithography, so you know how you can make elements like this. You make SU8 mold, and then you pour the PDMS over it. You guys did a little bit of that in the lab, and you can make this green element here. So this would be the top element. In this case, is the control channel. You're flowing gas through here, either maintaining this at high or low pressure. Then you have a second layer of PDMS, and this is the thin layer, shown in sort of the gold color. Now, this is also done with an SU8 layer. However, the layer of the PDMS, the thickness of the PDMS layer is only maybe 50 to 100 microns thicker than the SU8 around it. So what you end up getting is a pattern that looks, you'll end up getting, well, first of all, this will be rectangular. Initially, it won't be circular unless you reflow the photoresist. Photoresist pattern will initially be a rectangle, right? Now, let me just draw a quick diagram so we're absolutely clear on this. So in the soft lithography process, let's say you put your photoresist on here like this. So this is photoresist, or SU8, and this is your substrate here. Okay, and then you if you want to make a standard microfluidic channel, you would basically pour PDMS over this entire region, and this would become your channel. When you remove the PDMS, you'll have a channel that's the negative replica of this. Now in this case, what you're doing, instead of pouring on a thick layer, you're spinning on a very thin layer, and that layer is just thin enough to just be a little bit taller than the photoresist. So when you take this PDMS layer off, you're going to end up with something that's thick in these regions, but in the regions where you have the photoresist, there'll be a thin membrane layer. Now the dimension here is somewhere on the order of 50 to 200 microns. You can even make it a little bit smaller if you're very careful. So this is the key part here. You're able to make a membrane this way. So the membrane region is made this way. If you heat up the photoresist and you melt it a little bit, you reflow it, you can get this rounded pattern instead. The most common, this type of push-down valve is used when you need the flow layer to be in direct contact with the substrate below. So in this case, your flow layer, if you want that thing to be at the bottom, then you can use this type of design. So a more common design is the push-up valve. In the case of the push-up valve, the gas line, the pneumatic control line, is actually below the flow channel. Okay. So you have, your thin PDMS layer looks like this. It's a rectangle. So in this case, you don't do the reflow of the photoresist. But in the upper layer, you do a reflow so that you end up getting like a rounded profile like this. Now, can anyone think of why you're rounding? Why are we making the upper channel round? Think about how the valve is going to move.
Did it get more pressure on the button?
More pressure? Not quite. Not quite. Think about sealing.
So it's like flush at the top?
Exactly. Yeah. Yeah. If it's rounded, then when this membrane deforms, it's gonna deform into more of a hemispherical shape, right? So it'll form a better seal. So in fact, then it will be able to handle more pressure. So it's also correct. If it's a square profile, this type of valve, for example, has a square rectangular profile at the bottom and a rectangular profile at the top. When the valve deforms like this, it's going to leave some openings here. It's going to leave some leaking. So that's why the flow channel is often rounded. So this is, you basically apply pressure to the control channel. You can deform this. A few other variations: push-up, push-down valves. If you have the control channel in the middle between two fluid control layers, then the same control channel can be used to block this one and block the one below at the same time. And the sieve valves, which I just mentioned, they both have rectangular profiles, so that prevents a tight seal. So when you do activate the pressure here, it will deform but not seal the flow channel completely. So there's in situations where you want to avoid sealing the channel completely, that's the one that you would use. Excuse me. I forgot. I need a new battery for my phone. Just battery life is like 3 hours. Okay. Any questions on the Quake valves? If you go to the Stanford Microfluidics Foundry, you'll see a video on, there's videos here and there's many design guidelines on how to design these things. We're not going to go into all the details of this, but if you're interested, you can read about this. One of the things that you'll get from this is you'll see that this type of valve technology, it was invented in the early 2000s, and it's actually relatively mature right now. A lot of folks in the microfluidics community do use this valve technology. It's probably the most common valve technology you'll see in all devices. So this gives you an idea of some of the design rules, how small you can make these valves, what's the amount of pressure that you need to actuate them. A couple principles here. The larger you make, the smaller you make the valve, the larger the pressure you need to close the valve. All right, imagine if you have a membrane here, and let's say this is the channel region. Okay, so this is the gas layer. This is the membrane in the middle, and this is the this is the fluid layer. So this is the fluid layer. This is also the fluid layer. In one case, when we're talking about the size of the valve, we're talking about how much the area of the valve has, to deform and to block off flow in the fluid beneath it. So if we looked at this from the top view, this valve would look like this, and this larger valve, you have a larger channel below it, would look like this. Just by looking at this, which one's going to be easier to deform? The small one or the larger one? The larger one's going to be easier to deform. That's right. Because the total force on the membrane is equal to the pressure times the area. Right? This gas is coming in at a fixed pressure. In the large valve, the force is equal to the pressure over the area. This is a small area. This is a larger area. So the total force on the membrane is obviously going to be larger with the larger the membrane is, or the larger that the valve region is. So as a result, you can see some of these guidelines here. Is that if you have a 200 by 200 micron valve, the closing pressure is going to be 5 psi. But if you decrease that to 100 by 100 micron valve, your closing pressure is going to be larger. It'll be 10 psi. And if you go to even smaller valves, like 20 by 20 micron valves, the pressure will go up quite rapidly to 50, 60, 70 psi or more. So that's just something to keep in mind, because as we'll see in the next slides, trying to put a lot of valves on the chip, the more valves you have on the chip, the more fluid you're able to control, the more complex flow control that you can do. However, if you want to get a lot of valves on a chip, you need to make them small. That means you're going to need to use larger pressure to actuate them. So it's just something about the design concepts here. Another important thing is if you want a good seal, the aspect ratio of the channels should be less than 0.1. So in this case, this channel is going to seal much better than this channel. You can imagine when this deforms, it's going to look something like this. When this deforms, it'll look, it'll look something more like this. So wide and short channels are better than tall and narrow channels if you're trying to seal them from above. Okay, so let's talk about some of the follow-on work. This is actually this last paper done here, Microfluidic large-scale integration. It's one of the famous papers in the field. In this paper, this is also Stephen Quake's group, they showed that these valves are very scalable. You can you can put many of these valves on a chip. Some of their chips demonstrated that you can make like thousands of them on a chip. And moreover, you can use these valves in a clever way to create some fluid control elements, namely multiplexers. So we already know about how the valves work. So let's look at this something called a binary multiplexer. All right, so let me explain the structure of this region first. All the vertical lines here are fluid channels. Now what we're trying to do, the objective here is to design a device where you have 7 fluid inputs, but only a single one of those fluids gets to go to the output. So that's what a multiplexer is. You're selecting one of the inputs to go to the output. So this is a way to do that, using these horizontal lines, which are the pneumatic control lines. Remember, the pneumatic control lines are on a different layer. So ordinarily, if you think about it, if we wanted to make let's say we had 4 channels here. And we want to create a multiplexer out of this. So we want to select which 4 of the inputs we're going to direct to the output. All right. One simple way to do that would be to have 4 control lines. So this is one valve. So on the horizontal lines, maybe I should draw this in a different color so you can see the difference here. So the red channels will be the control channels. So one way we could do that is by putting a valve here. We could put another valve here, another valve here, and another valve here. Each one of these would be connected to their own respective control channels. Right, each one of these circles would be an inlet where we could, have a syringe in there to put in a certain gas pressure. If this channel is pressurized, for example, then this channel will be blocked. It won't allow fluid flow. So 4 channels would require 4 fluid channels would require 4 gas control inputs. Right? This is fine. This is simple. It works beautifully. However, if we want to control, let's say we have 16 input channels, so there's 16 blue input channels, or 32 or 64, like if we have many, many fluid channels and we want to be able to multiplex that out to one input, this one-to-one relationship doesn't really work very well. So let's say for 100 fluid channels, you need 100 control inputs. 100 control, that's a lot of control inputs to manage. Right? So the Quake's scheme, which is really brilliant, it uses a binary encoding mechanism. So they make the pneumatic channel wider in certain patterns, in certain regions here. Okay, so in the regions that are wider, these valves have a larger area, so they're able to deform at a certain amount of pressure. Also, you have several control channels going across like this, but you notice that these widened regions are in a very specific pattern. Okay, and if you remember binary numbers, you'll see that this is sort of a binary pattern, where like if you're looking at a 3-bit binary number, then this will represent the most significant bit, and these ones will represent the least significant bit. If that doesn't make sense, don't worry about it. But the idea here is that based on this pattern in which the control channels are laid out on top of the fluidic channels, you can give a binary code to the control channels and get a single output here like this. Now, ordinarily, with if you had 8 fluid channels, if we didn't use the binary multiplexing scheme, we would need 8 gas control channels, right? 1 for each fluid channel. But with this Quake scheme, n fluidic channels can be controlled by 2 times log n control lines. All right, so when your n becomes very large, when you have many fluid channels, the number of control lines that you need is only 2 log n. So it really saves you in terms of the number of control channels. This example is only 7 channels, so it doesn't do a great job of illustrating the benefits of scaling, right? Because you know, this is 8. So to control 8 channel lines, we have 2 log 2 to the 8. Now this is log 2 to the 8 is of 8 is 3 times 2 is 6. So to control 8 channels, we only need 6 control inputs. So that's not that impressive. But if you're talking about you know, controlling 64 or 100 channels or 200 channels, then you'll see a huge difference in the number of control channels that you need. All right, so how the multiplexing scheme works, this is an example that's given here. In order to select one of these lines, so if I want to select 3, for example, I have to put a 3-bit binary code. So I have to, if you convert 3 to binary, it's 0, 1, 1. Now binary, of course, is base 2. Now, for each one of the bits, there are 2 corresponding pneumatic control lines. This is bit 3, and this is the opposite of bit 3. Okay, so if bit 3 is, if you want to select channel 3, the binary code for this is 0, 1, 1. So bit 3 is equal to 0. If bit 3 is equal to 0, that means that this pneumatic channel is active, and it's blocking these 4. And this channel, this pneumatic is not active. So it allows fluid flow through all of these. All right, so if we're going to, if we want to select one channel out of 8, the first thing we'd probably want to do is, like, if you want to think of a divide and conquer scheme, right? Okay, the first bit is telling you whether it's greater than 4 or less than 3. You're controlling, you know, by setting bit 3 equal to 0, you're closing off all 4 of these channels. The second bit is equal to 1, so that means the top one is active and the bottom one is not active. So in this scheme, this also blocks off 4 channels, but not the same ones as the first bit. And this is allowing, this one allows 2, 3, 6, and 7 to pass through. Bit 1 is equal to 1, so this one has 4 channels that are blocked off like this, and then 4 that are open like this. Okay. Now, when this pattern, remember, in order for a fluid to flow from input to output, it has to have an open path, meaning everything needs to be open, even if one of them is blocked. You know, for example, even here, just one of them is blocked. That's enough to block the fluid flow. They all have to be open. All right, so you can look at this at home. This is a very clever scheme. It allows you to put in a 3-bit code. So 0, 1, 1, and basically a 3-bit code means that this is at, you know, it tells you what the pressure values of these pneumatic lines will be, whether the pressure will be high, let's say 10 psi, or low, which means 0 psi. All right, based on those pneumatic inputs, you can control the multiplexer lines. So this technology, this approach can be scaled to very impressive proportions. It enables like thousands of valves to be integrated on a microfluidic chip. The technology is actually commercialized by a company called Fluidigm, which was started by Stephen Quake, and they're based out in the Bay Area. This particular chip, they had literally thousands of valves that were all controlled by multiplexers. So they only needed a limited number of gas control lines. And the valves were basically controlling the sample that went into a chamber and when it was released by the chamber. And in this device they had, I don't remember the number right now, but it was several hundred, probably more than 1,000 individual chambers that could be sealed off by valves using the multiplexer approach. This is another example which we just saw in the previous module, where you have a whole bunch of valves on a chip, and you're using those valves as peristaltic pumps, and you're using the valves to control the flow of liquid from one place to another. You can see this sort of pattern here. This is that binary multiplexer scheme. Now, in this binary multiplexer, they've actually injected black liquid into the channels so that you can clearly see where the valves are. Otherwise, PDMS's transparency would be difficult to see. So these aren't fluid lines. They're actually the gas pneumatic control lines. So there should be only gas filled in the channel. So this is just an illustrative. It's an illustrative picture. So these types of devices, by the way, the reason why they've been commercialized is because if you have a lot of individual chambers, and those chambers, you can direct the flow into each one of those chambers, and you can make each one of those chambers become a chemical reaction. It can be used for a different chemical reaction. In Fluidigm's device, they have a system that has maybe 96 multiplied by 96 individual chambers. And each one of those chambers is used for amplifying DNA. It's used in something called digital PCR. And that product has, it leverages the fact that there are so many chambers where you can control the liquids going in and out. So there are new biological protocols that are literally being enabled by technology like this. Another example of where microfluidic valves can be used. So I mentioned this thing about chambers. This is another one of Stephen Quake's work, which sort of nicely illustrates how you can get fluid into individual chambers, seal those chambers off, and to get these individual basically containers where you can do biological assays and biological screening. So, Priyan, you'll find this interesting, I think, also because it is somewhat related to the project that you're working on right now. It's electrical memory. There's something called the row column addressing. If any of you have looked at how RAM, random access memory works or flash memory works, if you want to store a piece of data, you have to tell the chip that I want to store this piece of data in row X and column Y. And it goes and it stores the data into that specific area within your flash memory chip. Right. So Quake applied that concept of a row column addressing scheme into a microfluidic chip. So you can tell the microfluidic chip into which row and which column you want to store something. So how this microfluidic memory thing works, in this particular demonstration, they were just trying to show something like this, where you can fill selected chambers with, in this case, just a specific dye. Right, but ultimately this dye would, it wouldn't be just a chemical dye. It would contain some type of biological assay. Like, for example, a single cell assay, which their company has actually done. So they wanted to show that you can selectively load samples into selected chambers within a big array. So they use their valves. They use their multiplexing scheme, as you can see here. They had two multiplexers in this case. They had a row multiplexer and a column multiplexer. And they had some different fluidic inputs, which we'll talk about in just a second. So the row multiplexer allows you to, let's say if you have, in this case they had a 25 by 40 array, and so there's 25 rows here and 40 columns here, giving a total of 1,000 chambers. So 25 columns can be controlled by 2 times log base 2 of 25. All right, so not that, a total of 22 outside gas regulators were needed. And these gas regulators are only about this big, so it's quite possible to have a stack of 22 of them to control all the gas pressures. Because remember, the microfluidic, this type of multiplexer approach requires one pressure regulator, which is external, for each one of these gold rows. Okay, each one of these is connected to a pneumatic input. And by the way, those pneumatic pressure controllers are solenoid, based on solenoid valves. All right, but let's get into the how you would want to load this device. So the loading procedure looks something like this. First of all rows, in all rows you fill the middle channel. So each row actually consists of 3 sub-rows within it. Okay, so this is one row segment of your microfluidic memory device. And you can see that there's some vertical valves, and then there's some horizontal ones. So there's 2 horizontal valves and 2 vertical valves per chamber. So the loading procedure looks something like this. In all the rows, you fill the middle channel with A. So the middle channel would be this one here. So initially, each one of these, all the column valves are closed, and the row valve, the middle row valve, is open. So this allows you to fill all the rows of the microfluidic memory. So all the rows are filled with the dye that you're looking for, or the dye that you want to fill it with. And then what you do is you will selectively purge the ones that you don't want. Right, so this yellow line shows what happens next. First, the row multiplexer directs fluid B to the lower channel of the selected row. Fluid B is a buffer. Fluid A is a dye. So fluid B is just being used to purge or clean out one of the chambers. So what happens here is the particular rows, this happens one row at a time. Okay, so let's say we're handling this row. The particular columns that you would like to remove or purge, you open up the valves just in those, you open up the valve for that column, corresponding to that column, and you allow the liquid, the purged liquid, to flow through there into the upper channel, and so on. Okay, so that's the step 3. Column 3, the column multiplexer releases the vertical valves, allowing B to flow through a selected chamber and purge its contents. So you have a certain set of rows. The row multiplexer controls which rows are injected with the fluid, and the column multiplexers control which columns are filled with a certain fluid. So the row multiplexers and the column multiplexers work together to determine which one of these chambers in the 2-dimensional array will be filled and which ones will remain empty. All right, so the first time I looked at this one, it was just over my head. Look at this the second and third time, and it'll start to make sense. But it's really beautiful work because it shows you that in this particular device they had 3,500 valves in the system, and they had 1,000 individual chambers which could be individually controlled. right? And this was all done with 22 pneumatic regulators on the outside of the chip. Very nice work. So let's see. Would you all like to take a short break? Or shall we just keep on going for another 20 minutes and maybe end class a little early today? Any opinion? What do you prefer?
Push through.
Push through? Okay. All right. Nick is vocal, so it's his choice. All right, we'll try to end a few minutes early today. So let's talk about different types of valves, just to give you an idea that there are some variations to the standard Quake valves that have become so popular. You know, you can see one of the downsides or one of the challenges with Quake valves is that if you want to get a good seal, you have to get this rounded profile, which means you have to reflow your photoresist. There are other ways that you can get a nice seal in valve technology, and that's by using something called doormat valves. The doormat valves use a 3-layer design. This is similar to what you're working on. Excuse me. Where you have a thin PDMS membrane sandwiched between the control layer and the flow layer. So you have one layer of PDMS that looks like this. This is where your fluid will flow, and then you have a thin PDMS membrane, and then you have a third layer below where your control channels are, and these are the ones that will be filled with gas. Now, these membranes are flexible, so if you were to apply a pressure going from left to right, the pressure itself would open up, would cause the valve to distend down like this, and you would allow fluid flow to go through here in this direction. Okay. Now, if you apply vacuum to the control channel, that'll help the process out even more. So if you apply vacuum here, that'll pull these membranes down, and it'll allow fluid to flow through here. If you apply positive pressure to it, then this membrane will be pushed towards a post, and this post is called the valve seat. The terminology is the valve seat, or the boss. Sometimes they call it a valve boss. That will obviously prevent the flow going through the channel. Now, this is a membrane that's being pushed down onto a post, so there's actually a very good contact that happens between here, so these valves form very good seals. That's one of the advantages of these doormat valves. They are slightly larger, but they can be made small as well. So these valves are normally closed, whereas the standard Quake valves are normally open, and they require a vacuum to open the valve, generally about -5 to 10 psi. Another example, the less obvious advantage to these things is that there's no curvature in the main chamber. For example, if you are using a Quake valve, and the Quake valve, let's say this is your chamber, when this valve distends upwards like this, that may cause a distortion in your optical signal if you're trying to look at the chip from above. So that's less of an issue with these valves because the distension part is kind of on the outside here, so the chamber is here like this. Okay, the downside with these valves is that when you bond your PDMS layer, remember I said when you bond 2 layers of PDMS, they stick to each other, right? You treat it with oxygen plasma, and then the two PDMS layers form a bond with each other. Well, turns out that this thing here, when this PDMS touches this membrane, that also bonds. So you actually have to do a deactivation here to prevent these posts from binding. And Priyan has actually found a way around that, right? So, That's why. Interesting technology Priyan's working on. All right, another type of valve is which avoids the multi-layer completely is these sidewall valves. Okay. And this doesn't require multiple layers. It's sort of easy to see and easy to understand. Imagine these are all microfluidic channels, the gray regions. Okay, let's say you have something like this, which looks like you have your gas input on the side here, and you have the flow input. This is your fluid channel. And this one here, these two things here are your pneumatic channel, your pneumatic control channels. When you apply a positive pressure here, this causes the membrane, or membrane meaning like the thin wall between the gas and the fluid flow layer, it causes it to bend this way. Okay, and when these two things bend, it can close off the microchannel. So this is a very simple way to get valves in a single layer device. All right, and they've shown examples of where these deformable membranes can be used to direct fluid flow from one direction to the other. These pictures are a little bit hard to see, but they're basically showing a bead going directed to one outlet versus the other outlet as a result of these valves. So what you're doing here is you're flowing in fluid and your particles in the bottom half of the channel. And if you close off this channel, then the flow is all going to go to the right. If you close off this channel, then the flow is all going to go to the left. So you just have a way of controlling and sorting the particles. So these things don't actually entirely seal the channel, but they act as a flow resistor, meaning they just change the fluidic resistance of one channel versus the other. So it's the equivalent of a potentiometer. The circuit equivalent would be a potentiometer. Latching microvalves. So these are interesting devices. Now, how many of you have any of you taken a class in digital logic? Okay, how many do you have? So in digital logic, do you remember the concept of a latch? Latches and flip-flops. So yeah, it's okay. I'm putting you on the spot here. They're devices that they're gates that maintain state. Right. Whatever state, whether it was in a 1 state or a 0 state, it has the ability to remember its state. So it's the basic building block for memory. So latches and flip-flops have the ability to remember if they're in a state A or state B, one of two states. Okay. Turns out there's a pneumatic equivalent of that also. It's a pneumatic circuit, a microchannel circuit that is able to remember its own state. So if you were to initially set this device to a high pressure, it will remain at high pressure, and if you set it at low pressure, it will remain at low pressure. It will remember its pressure state. I'll show you on the next slide where these types of circuits come in handy. This is what it looks like in the electrical domain. So this is for if you want to like read about flip-flops, you can do this. This remembers if you apply a pulse at the reset input, it'll go into the off state, and if you apply a pulse to the set input, it'll go into the on state. On state meaning like this has a high value, Q bar has a low value, and then if you reset it, this has a high value, this has a low value. So in terms of pneumatics, okay, latching microvalves use feedback to maintain the valve in the closed or the open position. All right, and it uses a pneumatic circuit very similar to this electrical circuit here, where we have two cross-coupled transistors, and the output of one transistor feeds back to the input of the other transistor. Now, the pneumatic equivalent of a transistor is something like this, the doormat valve. Okay, a transistor is, you can think about a transistor as a switch, exactly. A switch or a relay. Okay. Um, if you apply, in a transistor, if you apply a high voltage here, then this transistor will turn on, and that will allow current flow this way. So by applying a high voltage here, you're basically flipping the switch. You're turning on the switch, and you're allowing current to flow like this. Okay, this concept applies to whether you're talking about bipolar transistors or MOSFETs, whatever.
One of them is working on the saturation and when the transistor is under saturation, and one other one is when
I think let's not get into the saturation versus the triode region, because that gets into the more of the analog properties of the transistor. I just want to explain things at a very high level, just so we can understand the pneumatic equivalent. So the basic idea is this: you apply a high voltage here, and that turns the transistor on, so it allows current flow between these two elements. If you apply a low voltage here, this turns the transistor off, and it blocks any current flow between these two elements, because it's a switch. Now, the way that you can implement a switch in a microfluidic device is exactly what we just showed with the doormat valves. If you apply a vacuum here, then you get current flow between the input and the output. If you apply positive pressure or even a zero pressure, you block the flow, and you do not allow flow between the input and the output. So you see that a valve like this, okay, a microfluidic valve is the equivalent, or doormat valve is the equivalent of a fluidic transistor. Now, the reason why that's cool is if you think about the field of electronics, our microprocessors, all the things that form very complex computation, it's able to add numbers, it's able to save numbers, it's able to just do tremendous amounts of computational power. There's more computational power in the microprocessor in your cell phone than there was in entire rooms full of computers back in the 1980s or 1970s. There's a tremendous amount of computational power in microprocessors because there's a whole bunch of transistors on there. There's over 1 billion transistors on a typical microprocessor. Those transistors are organized into these things called logic gates. The logic gates can perform computations. There's things called AND gates and OR gates and inverters and things like that. And these things are organized into structures that can perform higher level computational tasks like addition and subtraction and multiplication and other types of computational. That's why they're called computers, right? So it turns out that if you create the pneumatic equivalent of a transistor, you can put these blocks together to make the pneumatic equivalent of a computer, to make pneumatic computers. It's pretty interesting. So let me talk first about how the valve works. This type of valve is inspired by an electrical circuit where you have two transistors where the output of one transistor is connected to the input of the next one. So they feed back upon each other. And this is something that maintains a specific state, as I mentioned. Now it turns out you can make a pneumatic equivalent of that by having two cross-coupled valve structures. Okay, and both of the valve structures are these doormat type valves. Okay, so this is one channel input. This is that little post that goes in the middle. Right, so this post here, the valve seat, is represented by this middle section here. And then you have another output here on the end. You have your thin PDMS membrane, and then you have the displacement chamber. So they made its latching valve in a two-layer device, which basically mimicked this electrical circuit. So they had one layer look like this, the other one looked like this. So the complete latching valve looked like this. There's a doormat valve here, a doormat valve here, and a doormat valve here. Notice that the top layer has a doormat, the doormat and the seat are in this region and in this region, but this part of the valve contains the doormat in the bottom layer. Okay, next more important concept is look at how these things are connected to one another. This, this is one valve, so you can either block or open the communication between these two sides. You can block and open communication between these two sides. But the output of this valve is connected to the input of this valve. And the output of this valve is connected to the input of this valve. So these valves are actually cross-coupled with one another in a manner similar to this system here. So as a result, you can build what's called a fluidic latch, where you can put a pulse input on here, meaning like, just a high pressure back to low pressure, square wave like this, and you can switch the state of the valve from the low state from the off state to the on state. In other words, if we're talking about it in pneumatic terms, from the open state to the closed state. So this bottom part of it, this is where the fluidic channel is, okay? You just want to control flow between the fluid channel, this left inlet and the right outlet here, and this is the valve part of it that controls it. So the trick that we're doing here with these two things is that we want it to maintain the state. If we put it into the open state where fluid can flow between between these inlet and outlet, we want it to remain in that open state. And when we put it into the closed state, we want it to remain closed. We want it to remain in these states even when the pressure is removed from the system. So in principle, even if you disconnected it from everything, it should still maintain that state. Now in reality, these things don't do that because PDMS is gas permeable, so the gas leaks through the PDMS, so it doesn't quite work permanently, but it does remain in the latch state for some period of time. We can go through the different parts of this, but I think we should I just focus on the main concepts here. You have a cross-coupled valve. So when the output of one valve goes high, that controls the input to the next valve, and that helps it maintain this type of state. There's a feedback that happens. Now, going back to the discussion I was making earlier, if you can create the fluidic equivalent of a transistor, then the next thing that people consider is that how can you make complex computation by putting those transistors into more complicated circuits and logic gates and things like that. And that's what the work that I recently saw that was published in PNAS in 2013, and there's some earlier work in that area too. Shu Takayama's group, who's at Michigan, he developed fluidic oscillators. Fluidic oscillators are circuits that are similar to this. Right? Similar to this, the fluidic oscillators can oscillate on their own from high to low. They'll resonate at a specific frequency. If this circuit is tuned appropriately, you actually have to have some capacitances in here too. So you can make the fluidic equivalent of that, and create fluidic oscillators. I don't have the picture of that in here, but another thing you can do with this is create digital circuits. Digital circuits include AND gates, OR gates, inverters, and it turns out that you can also make something called ring oscillators. If you take a bunch of inverters and you cascade an odd number of them together, and you connect the outputs to the inputs, you can get something called a ring oscillator. Let's go. We have a few minutes here, so we'll just touch on this concept really quickly. First of all, what is an inverter? An inverter is something that inverts the input. Okay, so in an electrical circuit, if you have a high voltage input, it'll give you a low voltage output. In a pneumatic circuit, if you have a high pressure input, it'll give you a low pressure output. Okay, so this is the electrical circuit. This is the fluidic equivalent of that circuit. You can see that a resistor in the fluidic circuit is just a long channel in the pneumatic device. All right, so there is this concept that if you want to make an oscillator in electronics, the symbol for an inverter in electronics is this thing right here. Okay, so if this is a high voltage, the output will give you a low voltage. And if it's a low input, then it'll give you a high output. Okay? So if you cascade an odd number of these inverters together, okay, let's say I cascaded 3 of them together like this. This is, let's say this input is high. What's going to be the next one is low. What's the next one going to be? High. And then what's the next one going to be? Low. All right. Now the trick is we can connect the output of this back into the input of this. So this is initially this is high, and so you get low here and then high here. And then the output of this inverter drives this thing low. All right, so now your low signal propagates through here. Now this is low. Okay, and then the next inverter becomes high. The next inverter becomes low. This becomes high. And this flips the input again. Okay, so a ring oscillator is nothing more than a bunch of inverters, an odd number of inverters that are connected in series, cascaded with one another. And basically what will happen is that over time is that if you choose any one of these things, over time it'll go from high to low. All right, it'll give a voltage pattern that just goes high to low. So this would be time on the x-axis, and then the voltage output on the y-axis. It'll just go high to low over time. And the frequency, or the period, t, between the oscillations depends on the propagation delay through the inverter and the number of inverter elements that you have. So this very awesome work that I saw some of these movies like a few weeks ago actually at a talk that Elliot Hui, the person who did this, he gave a talk in Ann Arbor on this technology. So he showed some cool videos, and these videos were up on the PNAS website, so I thought I'd share them with you. So he can make the fluidic equivalent of, can everyone see this? The fluidic equivalent of oscillators. Now, it's a little bit hard to see. I'm going to do this. Thank you. Oh, thanks, Brian. Appreciate that. I'm going to make this a little bit larger. Maybe this will help. Just look at the ones up here. So he has 3 inverters cascaded next to each other, and you see how these little bright spots appearing here? Those bright spots are the valves distending, going up and down. So this is a fluidic oscillator operating at 3 Hertz, and this is a fluidic oscillator that's operating at 2.3 Hertz, and these are the faster ones down here. Now the way that he controls the speed of these things is by controlling the resistances, or the lengths of these fluidic channels. So that changes the equivalent resistance here. So it's really cool that you can make pneumatic oscillators out of in the same manner by just taking this inspiration from electronics. Now, what can you do with these things? Well, you can make, if these chips are creating an oscillating flow pattern just based on a single pressure input. You apply vacuum to the device and it just starts oscillating on its own. So one thing you can do with that is if you have 3, if you have oscillators, you can use those oscillators to control diaphragms here, and you can create a pump out of them. So he used these oscillators basically to control these valves at different times, And if you pump 3 valves in succession with one another, you'll get what's called a peristaltic pump. And you can see that you get a nice pumping effect. So this is really neat. Yeah, these types of pneumatic circuit technologies can lead to integrated or smart microfluidic chips that not only have integrated pumps and valves, but these pumps and valves can control themselves. This requires no external pneumatic control other than just a single pressure input, or a single vacuum input rather, which is relatively easy to do. All right, so I said that we were going to end early, and I didn't, so sorry about that. But we'll pick up from here next time. We'll finish up talking about some microvalves, and then we'll get into different pumping mechanisms. So I will see you all on. I'll see you all on Monday. And if you have any questions, about the project, do let me know. If you have questions about the homework as well, let me know.
Are you going to be around tomorrow?
I'm sorry?
Are you going to be around tomorrow?
Yes, I will be around tomorrow afternoon. I should be around. Looks like. What is this?